Hi guys, I wanted to show you something today that's extra special. So today I'm going to show you the origin of time dilation. Now Einstein came up with time dilation, but his equation gives you the answer. It shows you how much time dilation occurs and why that occurs because of velocity. And what I'm going to do is show you how we define velocity from the quantum mechanical perspective, and we substitute that in for Einstein's velocity, which then is going to give us the quantum mechanical origin of time dilation. It's going to give us the same answer as Einstein's time dilation, but it's going to show us where it comes from and why. So space-time is composed of qubits, and qubits are just these little x-y axes. They're these little, they're called block spheres, and they encode information with geometry. So just real quick, I went over this in a different video, but I'm going to show you just real quick how light moving relative to itself defines velocity. So imagine this is this little xy axis. Here's the x and here's the y, and these are little beams of light that are shooting out from the center, or from the origin of this little graph. So now imagine we have a beam of light that is shooting on the x-axis, and this is a radius of 1, so this is a unit circle. Now imagine we also have a beam of light moving at a 60-degree angle. If we ask, how far has this little angle of light moved relative to the x-axis? That's called the velocity component, which is Vx. It is equal to c, which is the speed of light, times the cosine of theta. That is just telling you how far this beam of light has moved relative to this little beam of light that is directly on the x-axis. Now, if we ask how much velocity does this encode in the y direction, that's the velocity in the y direction, it's just equal to the speed of light times the sine of theta. Sine and cosine are just telling you how far something has moved relative to the x-axis. That's cosine. How far this angle has moved relative to the y-axis is sine. So this is how we encode velocity using the speed of light. And space-time is composed of these little qubits, and the rate that these little quantum state vectors are spinning and orientated on these little bits of space-time, which are qubits or block spheres, that defines velocity using light, which is the most fundamental thing. It's the one thing in the universe that is timeless. So now in Einstein's time dilation, there's something called the Lorentz factor. This is where you put in the velocity into this part of the equation right here for v, and that will tell you how much time dilation occurs. Your motion through space and your motion through time always equals exactly the speed of light, no matter what. So the faster you move through space, the slower time goes, so that your motion through space and time is always exactly the speed of light. So now what we've done here is we've shown you that we've encoded velocity and in the x direction, and we've encoded velocity in the y direction using the speed of light. So now that we understand that we can use qubits and light moving relative to light at different angles, we can define velocity. Another way to think about this is everything in the universe is moving at only one speed. Everything is just these little arrows that are spinning on qubits, and that forms space-time, the structure of space-time. Everything, including every bit of you and me, every particle, everything is moving at exactly the speed of light. But velocity is speed, how fast you're going, and its direction. So if I have a beam of light on the x-axis that goes for a distance of 1, and I have a beam of light that goes at an angle for a distance of 1, and they've gone the same distance in the same amount of time, even though they're both going the same speed, they have different velocities, because velocity is how fast you're going, but also what direction. So now we've defined velocity on a qubit, and we know that now we can define velocity with the speed of light. Well, we go over here to Einstein's equation, where we see velocity, and instead of putting velocity there, we say that the rate that this little angle of this quantum state is compared to the x and y axis, that defines velocity. So instead of putting v in, we put d theta divided by dt. Now that looks fancy, but it's really not. All that is saying is that the angle of this little orientation, theta means the angle, relative to dt, and dt is just this little axis, that defines velocity. We can also show, and I won't give you too long of it, you guys can check this out yourself, d theta divided by dt is also equal to the angular frequency. So now that we know that d theta divided by dt is equal to angular frequency, and d theta divided by dt is equal to velocity, which is v. So we can now substitute angular frequency, w, for v, and the new time dilation equation is, the Lorentz factor is 1 divided by the square root of 1 minus angular frequency squared. This is the quantum mechanical origin of time dilation. Hope you can see this. Sorry, I got to lower it down a little bit. This is the quantum mechanical origin of time dilation. This will give you the exact same answer to infinite decimal points as Einstein's Lorentz factor, but this shows the origin. This shows why time dilation occurs. It calculates the exact same amount of time dilation as Einstein's, but it shows why. He was defining it with velocity, and we're defining velocity more fundamentally as quantum states on qubits. So this is a big day. I hope you guys enjoyed it. There's so much I want to tell you about, but I'm trying to give this to you in little bite-sized, digestible bits. But there's a lot more coming in the very near future. So if you get a chance, check this out. You can check it yourself and you'll see that it's accurate to infinite decimals. Thanks. Bye-bye.